All right, so the plan for today is to just finish up a last little bit in section 8.3, um, get rid of this bit, adding and subtracting rational expressions with like denominators, and then move on to 8.4, adding and subtracting rational expressions with unlike denominators. So that's the goal for today. Note that Unit 2 exam is due today at 11:59, so if you haven't completed it yet, make sure to get in there and do that promptly. And as I mentioned, for this exam and for the final, don't wait until the last day to complete the exam if at all possible. So just a reminder, the final will be available this Friday the 3rd through the following Friday the 10th. We have our last class meeting on Thursday the 2nd. That'll cover simplifying complex rational expressions on the 9th, next week, next Thursday. That's our scheduled final exam time. From 8:30 to 10:10, we'll have an optional review session. So I'll basically just treat this like office hours. Basically, I just have to offer some kind of something, what do they call it? Like something of educational value or something during that time, if we're going to do an exam like this, where it's going to be flexible online and you can take it when it works for you. So that'll be, I'll be available during that time if you have any questions, anything like that. But again, the final exam is Friday the 3rd through Friday the 10th. And there are no due date extensions, so make sure that you don't wait until the last minute to complete that exam. Okay, so wrapping up section 8.3, adding and subtracting rational expressions with like denominators. And we saw one of these on the worksheet last time, but just to go through and practice one more, where we have almost the same denominators, but not quite. And we notice that 1 minus 4x is negative 1 times 4x minus 1. And I know that, for instance, a over negative b is just negative a over b. I can move a negative sign from the numerator to the denominator to out in front of the fraction. They all mean the same thing. So this 1 minus 4x in the denominator of the second rational expression becomes a minus 1 times 4x minus 1 in that denominator. And then that minus 1 just comes out front to give us 18x over 4x minus 1, and then minus 6x plus 3 over 4x minus 1. So this minus 1 here is what changed the sign in front. And now we have two fractions, two rational expressions with like denominators. So what do? We add or subtract the numerators, keep the same denominator. So 18x minus, and I want to be careful here with the parentheses, minus this whole second numerator, 6x plus 3. Or this is 18x minus 6x is 12x. And then this minus also distributes to the 3 to give me minus 3 over 4x minus 1. I have now gotten down to a single rational expression, and now I want to simplify if possible. So I'm looking to factor, because remember, if I want to divide something out, I do not want to do something like, say, 12x over 4x equals 3 and do something like that. That wouldn't be a valid operation. I can only divide out common factors between the numerator and denominator. So I'm looking to factor everything. Well, the denominator doesn't factor. 4x minus 1 is just what it is, but there is a common factor of 3 in the numerator, leaving me with also 4x minus 1. Nicely enough, my factors of 4x minus 1 divide out, and I'm left with simply 3. So actually, after all of this, we just get the number 3. And I remember there was one more little detail that we wanted to be careful of. If I just left it here, I'm making the claim that this expression and the expression just the number 3 are the same thing, that for any x that I choose, if I plug it on the left side, I get the same answer as, well, I would say if I plugged it in on the right side, but there's really nowhere to plug it in there. So my claim, if I just left it like this, is that any real number x that I plug in on the left side, I simplify it down and I would get 3. But we know that that's not equal, that's not true. This equation does not hold for our restricted values. So what are our restricted values? That's the set of x's that we are not allowed to plug in. That's the set of x's that makes the denominator 0. And here I see that I have 4x minus 1 in the denominator. So when is 4x minus 1 equals 0? That's when x equals 1/4. So I just have to say x not equal to 1/4. And with that restriction, x not equal to 1/4, then now the left side does equal the right side. So that initial sum of two rational expressions, whatever value of x I plug in aside from 1/4, and when I simplify all of the numbers down, it will turn out to just be 3. Okay, let's do a quick practice problem on that. Two practice problems on that, sorry. Every time that I close OneNote and reopen it, it zooms everything out. So get the zoom fixed here, because I know, especially with these rational expressions, they're hard to see on the screen if they're not zoomed in. So, all right, let's take about 6 minutes or so, kind of get warmed up for section 8.4. We're going to deal with unlike denominators. Work through these two problems. Like usual, like usual, I will, wait a minute or so and then kind of start working through the problem. So if you get stuck somewhere, try to work it out yourself if you get stuck. But if you get stuck, you should see me catch up to you at some point, and then you can use my work to help you get unstuck and move on forward. So we'll take about 6 minutes, work through these ones. Actually, maybe closer to 5 minutes. Like denominators, we don't have to do quite as much work as the next section. So we'll take about 5 minutes for these two, and then come back and discuss them. Okay, so let's discuss this one and then we'll work through the next one. I kind of realized partway through that I wouldn't have enough room to actually work through both of them at the same time. So yeah, these problems that we're doing now take just a little bit more calculation, a little more work. So again, the key idea here is to recognize that these denominators are almost the same. They're just off by a factor of -1. So we can make the second rational expression 3x squared plus 4x minus 1 over 7x minus 4 if we pop that -1 out in front, that negative sign out in front. So we have now the difference of the two rational expressions, but they have the same denominator. So we take the difference of the numerators over 7x minus 4. And we just have to be very careful with our distributing the negative here. If you wanted to take an extra step and write out all the terms individually, minus 3x squared minus 4x plus 1, you could definitely do that. But here for our x squared terms, we have 10x squared minus 3x squared is 7x squared. We have 21x minus 4x plus 17x. And then -13 minus a -1, -13 plus 1 is -12. I want to factor this quadratic in the numerator. It's not a super easy quadratic to factor. So I'll use AC grouping. And I see that a times c is 7 times -12 or -84. I'm looking for two numbers m and n such that their product is -7 times 12 and their sum is 17. I'll factor -7 times 12 into its prime factors. That's a -1 times 2 times 2 times 3 times 7. Right, 7 is prime, and then 12 factors into 2 times 2 times 3. And this will make my my listing the potential m's and n's easier. So if I find two factors that make 84, that could be, say, 1 and 84, or 2, then I've used up one of these twos, and I'm left with 2 times 3 times 7, which gives me 6 times 7 is 42. 3 is a factor. If I use the 3 for m, then for n, I have 2 times 2 times 7, or 28. None of these look promising so far. Remember that we are looking for the product to be negative. So we want either m or n to be negative and the other one to be positive. So we're looking for a difference between m and n of something like 17. But our next one, we see that, do we have a factor of 4? Well, sure, we could use our two factors of 2 to make the 4. That would leave us with a 3 times 7, making a 21 for n. And that does give us a difference of positive 17 if we take plus 21 for n and minus 4 for m. So this one works. We'll come back over here and we will split. Remember, the whole idea here is that we split the middle term, the linear term, into mx plus nx. So that's the whole reason we find m and then we factor by grouping. So we split plus 17x into minus 4x plus 21x, or if you did plus 21x minus 4x, that's fine. You'd have a slightly different intermediate step, but you would get the same answer at the end. And then here I group my first two and my last two terms. For my first two terms, I note there's a greatest common factor of x. So I factor out x times 7x minus 4 is left over. And then for my last two terms, I know that there's a greatest common factor of 3 times 7x minus 4. And now in each of the two terms in the top, I have a factor of 7x minus 4 that can factor out, leaving me with 7x minus 4 times x plus 3. This factor of 7x minus 4 in the numerator cancels with that same factor of 7x minus 4 in the denominator. And I'm left with x plus 3. And once again, I have to just be very careful to explicitly note my restricted values. They're not implied in the right-hand side here. X plus 3 at a glance looks like you could plug in any real number, but there would be some numbers, or a number in this case, that would give me a 0 in the denominator in the original set of expressions. So for to stay away from having 4 minus 7x or 7x minus 4 equals 0, we just want to make sure to note the restriction x cannot be equal to 4/7. And this would be our answer. Okay, let's work through the next one. I think we did do this one at the end of last class, but I want to do it again today to kind of warm up a little bit, and because I think we did it a little quickly last time. Okay, so we look at this one and we have 5x over x squared plus 5x plus 6 minus 7x minus 4 over x squared plus 5x plus 6. So here we start off and we already have exactly the same denominator. We don't have to do any messing about like we had to do up here. We can right away just put everything over that common denominator. Again, I just want to be careful with that minus sign, that it does get distributed, but other than that, this should be pretty straightforward. So 5x minus 7x is a negative 2x. And then minus a negative 4 is a plus 4. And at this point, I've gotten down to a single rational expression. Now I want to factor everything, see if anything divides out, simplify as far as I can. I notice in the numerator, there is a factor of 2 that I can pull out. If I pull out a 2, that leaves me with negative x plus 4, or sorry, negative x plus 2. Often, I mean, that's not terrible, but often I like my factors to be positive, to have a positive coefficient of x. So I'm going to choose to pull out a negative 2 here. When I do this, it just helps me see a little bit more easily what the common factors are. So if I pull out a factor of negative 2, then I'm left with, for the first term, just an x. And for the second term, I have to be careful. I have a negative 2 left over. So negative 2 times negative 2 gives me my positive 4. And then x squared plus 5x plus 6. Here I'm looking for two numbers that multiply to 6 and that add to 5. I think that's going to be 2 and 3. Right, if I multiply this out, I get x squared for my first. My outsides and my insides give me a plus 5x, and my last give me a plus 6. So that looks right. So actually, see, I don't get anything that divides out here. And this is my final answer. I can leave it this way. I don't have to really necessarily explicitly state the restricted values, because x not equal to 2 and x not equal to 3 is implied here. If I wanted to state them, though, sorry, x not equal to negative 2 or negative 3. I swear these days that my allergies are like flaring up, usually for about a week or so. Sometimes I just have the worst brain fog. But x not equal to negative 2 or negative 3 in the denominator here, that's the same restricted values that we see in the original expression. So we could explicitly state them, or if we didn't explicitly state them, they're kind of implicitly stated through this expression here. So this is a bit simpler than the original expression, but not so much simpler as, you know, something like this or the last example that we saw. But even though we didn't divide anything out, it was still useful for us to factor everything and just double check that nothing did divide out. Okay, any questions on this so far? All right, give me 1 second. Okay, so moving over then to 8.4. Here we're looking at adding and subtracting rational expressions with unlike denominators. So just like we've done in the past, we note that rational expressions are really just kind of slightly more complicated fractions. So let's start with just numerical fractions. So if I had something like 1/3 plus 1/4, how would I handle that? Well, I know if I had something like, say, 1/6 plus, let's say 5/6, here I have a problem where I have the same denominator. I'm adding two fractions with the same denominator, so I keep the denominator and I add the numerators. And then I know that 6/6 is just 1. I know that any number over itself just ends up being 1. So all of this simplifies down to 1. So there's two ideas I want to make use of here. One is that if I can make an unlike denominator problem look like a like denominator problem, I kind of know how to solve that already. And I can leverage the fact that a over a equals 1 as long as a is not 0. So like 6/6 is 1, or 3/3 is 1, or if I have a over a, I can simplify that to 1. I can go this way, but this is an equal sign. I could also go this way. I could, if I chose to, rewrite the number 1 as 6/6 if I wanted, or 3/3, or -2/-2, whatever. I'm going to use both of these ideas here. So 1/3 plus 1/4, well, these don't have like denominators right now. But I might look at this and I might say, well, if I could multiply 3 by 4 and 4 by 3, well, that would just give me like, what, 1/12 plus 1/12. And here I know how to do this. I know this is just going to be 2/12 and so on, right? So it'd be nice if I could do that. But I have to be a little careful here. If I were to do this, if I were to just change my denominators from 3 to 12 and from 4 to 12, of course I've changed the value of the fraction, right? I would have two different values here than the two values that I started with. But how could I do something like this? Well, what I could do is, instead of just multiplying by 4 on the bottom, if I consider 1/3 times 4/4, well, here I've just multiplied by the number 1. And similarly, if I considered 1/4 times 3/3, here I've also multiplied by just the number 1. If I multiply by 1, I don't change the value. So I can do this. I can't just multiply the denominator by a number, but I could multiply numerator and denominator both by the same number. Now remember, our order of operations, multiplication division, comes before addition. So I simplify these bits first. If I multiply two fractions together, I multiply the numerators, then multiply the denominators. That gives me the new numerator, new denominator. So 1 times 4 is 4 in the numerator, and then 3 times 4 is 12 in the denominator. right? 1/3 of a whole pizza, if the pizza was cut into 12 slices, would be 4 out of those 12 slices of pizza. And similarly, 1/4 times 3/3, I get 1 times 3 equals 3 in the numerator, 4 times 3 equals 12 in the denominator. So by creatively multiplying by 1 as 4/4 in one case and 3/3 in a different case, I see that I've backed myself into a situation where I have the sum of two fractions with like denominators. That's an easier problem, like this one up here, that I know how to solve. I add the numerators now. I keep the same denominator, 7/12. 7 is a prime number. There are no factors of 7 and 12. So that is the simplest I can get. So what if I had something like 3/10 plus 1/6? Should I just try to get a denominator of 60? Would that be the kind of the easiest way to go? Well, it would work if I multiplied 3/10 by 6/6 and 1/6 by 10/10 and got a denominator of 60. I could do that. But the thing is that I would end up with much larger numbers than I really need to. I would end up on the back end at the very end of my problem when I'm trying to simplify, having to do a lot more factorization, a lot more canceling and dividing out and so on. And that's just going to be a more cumbersome process. I'm adding in more complexity than I need, and I'm going to have to take all of that away at the end. It wouldn't be the end of the world, but it would be a lot more work than I need to. So what might I do here? I might look for a lowest common denominator. 1 second. Okay, so I might ask the question, what is the smallest denominator that I could get that I could turn both fractions into equivalent fractions with that same denominator? How do I find an LCD? We've discussed this before, but let's review. So the process for finding an LCD is first we take each of our denominators, in this case 10 and 6. We write out their prime factorization. So 10 is 2 times 5, and 6 is 2 times, and then I'm going to come over here to a new column and write a 3. So the LCD is, I have a column for 2's, so I need a 2 there. I have a column for a 5, I need a 5 there. I have a column for 3, I need a 3 there. Hypothetically, if my 10 was, say, a 20 instead or something like that, I would have a second 2. I need a column for second 2's, so I would have another one here, but we don't have that case here. So 2 times 5 times 3 is 30. And furthermore, I note that 10 includes the 2 and the 5, so we need to supplement 10 with an extra factor of 3. It's missing that factor of 3 that is in the 6, but not in the 10. And 6 has a factor of 2 and 3 already, but it's missing the factor of 5. So we need to supplement the 6 with the factor of 5 to make a 30. So 3/10, I need to multiply by 3/3, so that 10 in the denominator picks up that extra factor of 3. But then I also have the factor of 3 in the numerator for the 3/3, so that overall I don't change the value of the fraction. And then I have 1/6. 6 needs to pick up a factor of 5 to make 30. But again, I don't want to just multiply by like 1/5 or something. That would change the value. I multiply by 5/5 to keep the same value. I do my multiplication before the addition. So I multiply across the top. 3 times 3 is 9. Over 10 times 3 is 30. And 1 times 5 is 5. Over 6 times 5 is 30. And now, almost like magic, I have an equivalent problem, but where I have the sum of two fractions with like denominators. And now I just add across the numerators. And keep the same denominator. Sorry, just 1 second. Okay, so I think one of the things where it's easy to get a little mixed up here is when we are multiplying here and here, the denominator changes. We end up with 10 times 3 or 6 times 5, we're changing the denominator. Where when we're adding fractions with like denominators, the denominator stays the same. The denominator in each of our starting two fractions was 30, and in the ending fraction is also 30. Where like 3/10 times 3/3, our starting two fractions had denominators of 10 and 3, and our resulting fraction has a denominator of 30. So it's just very important to be careful. When are we multiplying? When are we adding? When does the denominator change? When does it stay the same? It changes, generally speaking, when we're multiplying or dividing, and stays the same, generally speaking, when we're adding or subtracting fractions with like denominators. But after all this, we get 14 over 30. And then finally, the last thing we would do, we're down to a single fraction now. We would factor, we would write 14 and 30 as their prime factorization. 14 is 2 times 7, 30 is 2 times 3 times 5, which we have from over here. And then I look for common factors that can divide out. In this case, the 2 and the numerator and denominator divides out. And I'm left with 7 over 3 times 5, or 7 over 15. So if I look at this process, we did the previous one as a bit of a warm-up, but if I consider this process, I have two fractions with unlike denominators that I want to add or subtract. I find an LCD, which I get by taking each of the denominators separately, factoring them, and then looking at what do I need to supplement in the one denominator or the other to get my LCD. I multiply numerator and denominator of each fraction by what it needs to have supplemented in the denominator to get the LCD, lowest common denominator. And then from that point, I combine my fractions together, and then I have the sum or difference of two fractions with like denominators. Then I can just add or subtract across the numerator, keep the same denominator. That gets me a single fraction. And then when I have the single fraction, I just factor and simplify. Okay, so, I mean, that's a lot of steps, but if we remember the strategy, it makes sense, right? If I just try to memorize, do this step, then this step, then this step, it's kind of hard to remember. But the same way that, if you were telling a story, if you were, telling somebody the general plot of Harry Potter or something, like, you're not going to get the fight with Voldemort before before Harry finds out he's a wizard, because it's not the way that the story progresses, right? So if we kind of know the overall idea, the overall story, so to speak, or the overall theme of what we're trying to do, then kind of the details fall into place a little more easily. So I would say, instead of just writing down steps and kind of rote memorizing the steps, and it's easy to get two of them backwards or something and get a little confused, understand overall the strategy that we're trying to do. We're trying to go from sum or difference of fractions with unlike denominators, which is kind of hard to deal with, to sum or difference of fractions with like denominators. This is really the key step. once we get to this step, from here on out, we kind of know how to approach the problem from previous work. So this last bit where we add and then simplify, that's kind of like, okay, I know how that works. So really the key is to get from unlike denominators to like denominators. And once we get there, we can kind of like take a deep breath and we're like, okay, I know how to do this from this point forward. All right, so let's do a problem where we have some monomials in the denominator. So here we have 5 over 3xy cubed plus 1 over 2x squared y. So here I have two fractions that I want to add together, two rational expressions, but they're just fractions. They have unlike denominators. 3xy cubed is not the same as 2x squared y. So my first goal, my kind of, sub goal is to convert each of these fractions into fractions that have like denominators as one another. So what do? I look for my lowest common denominator. I take each of my denominators, 3xy cubed and 2x squared y. And what does it mean to basically factor them like I did up here? Well, for the numbers, I could literally factor them, but 3 and 2 are just both prime. So their prime factorizations are just themselves. And then I suppose that if I really wanted to, I could write out, x times y times y times y. And then here I would need two x columns. So I'd have an x here and an x here times y. I could do this. This starts to look pretty messy. Especially you could imagine if I had an x to the 7th and a y to the 5th or something. I think it's going to be tough to keep all of my columns lined up and sorted out nicely. So I'll make a column for x's. And instead of x, I'll just write x to the first just to remind me that that's a power of 1. And then I'll make a column for my y's as well. Now I see I have a column for my 3. I have another column for my factor of 2. Now, how many x's do I need to include? Well, I need to include the number of x's, or the number of factors of x, that's the highest power. And same for the y's. I need the highest power because if I imagine that if I just had x and then another column for x, I would have two factors of x. I'd have two x columns. Or if I had y, another factor of y, and a third factor of y, I'd have 3 y columns that I would want to bring down. So if you're thinking of this column method for finding LCDs with numbers, we're really just taking each prime factor in some sense raised to the highest power that we see in any of the denominators. So in this case, we need two factors of x to kind of respect this x squared, and we need 3 factors of y for that y cubed. Now I realize that my first denominator, 3xy cubed, it's missing a factor of 2. It has one factor of x, but it needs 2 of them, so it's missing one factor of x. It has 3 factors of y, it needs 3 factors of y, it's good there. So my 3xy cubed needs to be supplemented with a 2x. And my 2x squared y, it's missing a 3. It has the 2 from the LCD. It has 2 factors of x. It needs 2 factors of x. It's good there. It has 1 factor of y, and it needs 3. So it needs to be supplemented with 2 factors of y. So my 2x squared y denominator needs to pick up a 3y squared in order to meet the lowest common denominator. So I have this fraction, and remember 3xy cubed, in order to turn it into the lowest common denominator, it needs to pick up factors of 2 and x. So we need to multiply it by 2x. But again, if we just multiply the bottom by 2x, we change the value of the fraction. So we need to multiply by 2x over 2x. So we're just multiplying by 1, not changing its value, but multiplying by 1 in a creative way that makes the next couple of steps easier. Similarly, with our second fraction, 1 over 2x squared y, it has a denominator of 2x squared y. It needs to be supplemented with 3y squared in order to make the lowest common denominator. I need to multiply by 3y squared on the bottom, but again, if I just multiply by 3y squared on the bottom, I would change the value. So to avoid changing the value, I need to also multiply by 3y squared on the top. Now, if I look at my first product here, remember I do multiplication before addition. If I'm multiplying two fractions, I multiply across the top. 5 times 2x gives me 10x. And I multiply across the bottom. 3 times 2 is 6, x squared, y cubed. That takes care of my first product. And my second product, multiplying across the top, 1 times 3y squared, 3y squared. And my denominator, 2 times 3 is 6, x squared, y cubed. And we now have the same denominator. We're now adding two fractions with like denominators. The numerators changed a little bit, and it was important to do all of this work to figure out exactly how the numerators needed to change. But now that we've got everything written as the sum of two fractions with like denominators, I can add the numerators and keep the same denominator. And now I can ask myself, well, the denominator is a monomial, so asking does anything factor out of it doesn't make a whole lot of sense. My numerator, 10x plus 3y squared, it's a binomial, but there are no common factors. There are no numerical common factors. 10 is 5 times 2, 3 is just 3, no common factors there. And then the x against the y squared in the two terms, no common factors there either. So this would be about the best we could do. Okay, so let's take a few minutes for a little bit of practice with these fractions with monomials in the denominator. The first one here is going to be quite similar to the one we just did. The second one's going to have a little bit of a hiccup or two thrown in. So it's a little more challenging, going to require a little bit more care and thought. So first one should look very similar to what we did. The second one will follow the same steps, the same strategy, but maybe there will be a couple of details, particularly when finding the lowest common denominator, that we'll just have to be a little careful about. So let's take about 6 minutes or so, work through these two, and then we'll come back and discuss. And as always, if you have questions in the meantime, you can always pop them in the chat, and I'm happy to answer. Okay, let's discuss these two. So for our first one, we have denominators of 5x y to the fourth and 3x cubed y squared. So the first thing we want to do is find an LCD, a lowest common denominator. And we look at 5x y to the fourth, and we have a factor of 5, a factor of x to the first power, and a factor of y to the fourth power. And 3x cubed y squared, we have a factor of 3, x cubed, and y squared. So, I mean, nothing super big that we need to do this first step. And then to get our LCD, we need a factor of 5 to satisfy this one. We need a factor of 3. We need some factors of x. How many? We take the highest power of x that we see, the third power. So x cubed. And then same thing with y's. We need some y's. How many? We need 4 factors of y. So our LCD is 15x cubed y to the fourth, or 5 times 3 x cubed y to the fourth. Now I note that my 5x y to the fourth, it does have the 5. It's missing a 3, so I need to supplement with a factor of 3 to make it into the LCD. It has 1 factor of x, but it needs 3 total, so it needs to pick up an extra 2 factors of x. I'm going to need to multiply, and it has 4 factors of y and needs 4 factors of y, so that's good. I'm going to need to multiply 5x y to the fourth by 3x squared in order to get my lowest common denominator. Similarly, for the second denominator, 3x cubed y squared, it needs a 3, it has a 3. It needs a 5, it doesn't have a 5. Well, we need to supplement with a factor of 5. It needs 3 factors of x, it has 3 factors of x, good there. It needs 4 factors of y, it only has 2. It needs to pick up 2 more. So 3x cubed y squared needs to be multiplied by 5y squared in order to make the lowest common denominator for that one. So coming back over here, my fraction 4 over 5xy to the fourth needs to be multiplied by 3x squared in the denominator to end up with like denominators or common denominators. But again, if we just multiply by 3x squared in the bottom, that changes the value of the fraction. We need to multiply by that same thing in the numerator. Similarly, for the second fraction, the second rational expression, 2 over 3x squared, x cubed y squared, I know that I've already worked out that I need to multiply that by 5y squared to make the LCD. And again, I do that on the top and bottom so I don't change the value of the fraction. Now I remember here that multiplication comes before addition. I want to be careful about that. And when I multiply fractions, I multiply the numerators to get the new numerator. I also multiply the denominators to get the new denominator. 4 times 3x squared gives me 12x squared. 5xy to the fourth times 3x squared gives me 15x cubed y to the fourth. That was my LCD that I had over here that I'm targeting. And then for my second two fractions, that second product, 2 times 5y squared gives me 10y squared. And the same thing as before in the denominator. 3 times 5 gives me 15, x cubed y to the fourth. So this looks a little messier, but the thing is that I now have 2 rational expressions with like denominators that are added together. Now I just add the numerators and importantly, keep the denominator. Don't make the mistake of adding the denominators together or something. It's an easy mistake to make because we just had multiplication a bunch of times, and for that we do multiply the denominators together. But now that we switch to addition, we add the numerators, keep the same denominator. And I want to investigate now that I've got everything under one fraction, I want to investigate whether there's any common factors that can divide out. The denominator is just a monomial. It doesn't have anything that can factor. The numerator is a binomial. we might be able to factor something out. We see that there's a greatest common factor of 2. We can factor out a factor of 2, but 15 is 3 times 5. Neither of those factors divides out with the 2, so we don't have anything we can divide out. We are done here. And I mean, as far as what's simpler, whether this black box or the blue box is the simpler form, I think is probably debatable. But I think this is the kind of preferred form, because it does kind of remind you to yourself that you did factor it, you did search for common factors, and you didn't find any. If you left it like this and you look back in your notes, the next day, you might say, wait, did I search for common factors and not find any, or did I just forget that step, right? But if you write it this way, you can pretty easily see that, okay, like there are no common factors. All right, just 1 second, and then we'll do the okay. So now the next problem, again, pretty similar type of problem, well, a very similar type of problem, but there are a couple of slight complexities here, particularly in finding the LCD. So let's look at our two numerators, 48y squared and 30x squared y. So the first thing we notice is that we actually have kind of complicated numbers to deal with here. So 48, its prime factorization isn't super easy. It's not like, 14 or something where you just like, oh, 2 times 7, and then we're right at 2 prime numbers. 48, well, if I want to get its prime factorization, I can factor it into, say, 6 times 8. And then I can recognize that 6 is 2 times 3, and 8 is 2 cubed. So if you have a bigger number, if you can, you can kind of chip away at it little by little, recognize that 48 has a factor of 2 in it, and then it's 2 times 24, and 24 also has a factor of 2. You could do that. It's kind of long and cumbersome. If you can split the number into 2 kind of equally sized factors, roughly equal size factors, it goes a lot quicker, because then each of those you can split pretty quickly. So recognizing 48 is 6 times 8, and then 6 is 2 times 3, and 8 is 2 times 2 times 2, I see right away that my prime factorization is 2 to the 4th times 3. And I will leave this in this kind of exponential form. So 48 factors into 2 to the 4th times 3. And then we have a 48y squared. So that y squared is just 2 factors of y. I'll just leave that as y squared. 30 factors into 6 times 5. And 6 equals 2 times 3. So 30 factors into 2 times 3 times 5. So we have a 2 to the 1st in the 2's column here, kind of. We have a 3 to the 1st and a 5 to the 1st. And then it's multiplied by x squared y. So we have 1 factor of y, 2 factors of x. So the first challenge was just getting prime factorizations for these slightly bigger numbers. This is something that we've done many times before, but sometimes something that you've done many times before, when you put it in a different context or when there's a lot else going on around it, it can become a little more difficult. So, but just realizing that, okay, we can just split this into those 2 problems. We can just do the prime factorization of 48 and of 30, forget about all the rest, just do those, get that out of the way, and then worry about all the x's and y's and all of that stuff separately. Now, the other thing we realize is that if we look at our columns, we have some 2's, 3's, 5's, x's, and y's. How many total factors of each do I need? I can just do kind of the same thing that I did with my x's and y's. I say, well, I have a 2 to the 1st and a 2 to the 4th. I need to pick the highest power, 2 to the 4th. The 3 and the 3 both just have a power of 1, so I just need 1 factor of 3. I see a factor of 5 in the second denominator, but not in the first. So I do need a factor of 5 in the lowest common denominator. And then for y, I see I have a power of 2, a power of 1. I need a y squared. For x, it might throw you off that my first fraction doesn't have any x's in it. 48y squared doesn't have any x's in it. Well, that's just kind of like this 5 here, right? Like one of the denominators had a 5, the other one didn't have a 5. We need to have a 5 in the LCD. One of my denominators has some x's, the other one doesn't have any x's. I need to have some x's in the LCD to make the second denominator happy, regardless of whether the first one has it or not. If you really wanted to push the issue, you could even put something like an x to the 0 and a 5 to the 0 here, and say that 5 to the 0 against 5 to the first, 1 is the bigger number, so we put a 5 to the first power, an exponent of 1 there. Or x squared against x to the 0, 2 is the bigger number, so we end up with an x squared in the LCD. So if you really wanted to push the issue, you could do something like that. But I don't think that's particularly necessary. Okay, so this is our LCD. 2 to the 4th times 3 times 5 times y squared times x squared. I see that 48y squared, it has a 2 to the 4th. It has a factor of 3, and I need a factor of 3. It does not have a factor of 5. I kind of put that in there. It makes it a little harder to see, but it doesn't have a factor of 5, but it needs a factor of 5. So it needs to have a factor of 5 multiplied onto supplement, and now it's good. It needs a y squared. It has a y squared. It needs an x squared. It has no x's. Again, I can just take that out. It needs an x squared. It has no x's. I need to supplement with an x squared. For my second denominator, 30x squared y, it needs 4 factors of 2. It has 1. It needs to pick up 3 factors of 2. It needs 1 factor of 3. It has a factor of 3. Great. It needs a factor of 5. Has a factor of 5. Also good. It needs 2 factors of y. It needs a y squared. It has a y to the first. It has only 1 factor. It needs to pick up 1 factor of y. And it needs 2 factors of x. It has 2 factors of x. Looking good there. So my first fraction needs to multiply by 5x squared over 5x squared. My second fraction by, let's call it 8y over 8y. 2 cubed times y over 2 cubed times y. As always, I know what I need to multiply the denominator by to make the LCD to get a like denominator. I also multiply the numerator by that to not change the value of the fraction. I do have a subtraction sign here, so just copy that down. And then for my second fraction, I need to know I know I need to multiply by 8y on the top and bottom. And that was the tricky part. Well, I suppose there have already been maybe 1 or 2 slightly tricky parts, but the part that's error prone in every one of these problems, I need to remember when I'm multiplying, I multiply the numerators to get the new numerator. I also multiply the denominators to get the new denominator. When I'm adding or subtracting fractions with like denominators, I keep the same denominator, but I add or subtract the numerator. So keep those 2 ideas separate in your head. But multiplying for these 2, multiplying the numerators, 7 5s is 35x squared. And in the denominator, I have 48y squared times 5. Well, one thing that I can do, 48 times 5, well, 48 is 24 times 2 times 5, or 24 times 10. So I can sometimes regroup some factors together to make nicer multiplications. 24 times 10 I know is 240. And then I get x squared y squared minus, multiply my numerators, 1 times 8y is 8y, 30 times 8, that's 10 times 3 times 8, 10 times 24, also 240, right? X squared, y squared. It's not a bad idea to do your denominator multiplications separately and then check that they actually match. I mean, in theory, they should match. In theory, I should just be able to figure out what my LCD is and just write it in the bottom here. But it's always good to actually do the multiplications here and just make sure that I didn't make any mistakes along the way. But I do get two denominators that do match, so looks good. And now I shift gears. Now I want to subtract two fractions with like denominators. I add or subtract the numerators and keep the same denominator. So you get 35x squared minus 8y, all divided by 240x squared y squared. My denominator is a monomial, so it's in a sense kind of already factored. My numerator is a binomial. I could, in theory, have some stuff factor out of it. I noticed that for the variables, I only have x's in the first and y's in the second term. So there's no variables that can factor out that are common factors. And I note that 35 is 7 times 5, two prime numbers, and 8 only has factors of 2. So there's going to be no common factors in the numerator that can factor out and potentially divide out with anything in the denominator. So that's that. That's as simple as it can get. Any questions on this? I know there are a lot of moving parts in these rational expressions problems. A lot of things to remember. This is kind of a capstone chapter for the course. It uses almost everything we learned in the course. So this is definitely not easy material. Okay, let's look at a problem like this. We want to simplify 3 over x plus 1 plus 5 over x minus 3. Now, what do I have here? Again, I have just two fractions added together with unlike denominators. So I have the same structure in that sense as, say, this problem or even my numerical fractions up here. What is different about this one? Well, what's different about this one is that I have a binomial in the denominator. I have the sum of two terms in each of the denominators, sum or difference of two terms, rather than having just like a single number or a monomial, a single term in the denominator. So when I think about coming over here and finding, say, an LCD, if I have x plus 1 and x minus 3 as my denominators, when I say find a factorization, like I did over here for, say, 3xy cubed, which was 3x to the first, y to the third, what is my factorization here? Or if I gave you this expression x plus 1 and said, factor this, well, we actually had a term for that where we can't factor it. And we called that prime, right? We called that prime polynomial, that it can't be factored. There's really just nothing to do with x plus 1. It's already just one factor. So it's just kind of like the 3 up here. It's already a prime number. It can't be factored. Or it's like the 3 or the 2 here. It's a prime component in some sense. this x plus 1 is like already as simple as it can get. It can't be broken down into the product of two things any more simply. And the same is true with x minus 3. So if I had one denominator that was a 3 and another denominator was a 5, the LCD would just be 3 times 5, because the 3 can't break down into any simpler factors, and neither can the 5. So the LCD is just the product of the two. Well, that's the case here as well. I have some x plus 1s, some of these prime factors in some sense. I need one of them to satisfy the first fraction, to satisfy 3 over x plus 1. I also have some x minus 3s. I have some of that prime factor. I have one of them in the second denominator, so I need to retain one of them in the LCD to satisfy that second fraction. Or my LCD is just x plus 1 times x minus 3, the product, in this case, of the two denominators. This is similar to how in 1/3 plus 1/4, our LCD was just 12, the product of the two denominators. So the underlying structure, the underlying methodology, whether we're dealing with numbers and finding LCDs, or monomials and finding LCDs, or binomials or polynomials and finding LCDs, the underlying ideas are the same. We break down into the smallest factors, the prime factors, and then we build our LCD from there. In this case, basically, in the sense of polynomials, our denominators are just prime. They're equivalent to the idea that if we just had prime numbers like 1/3 plus 1/5, our LCD would be 3 times 5. If we have 3 over x plus 1 plus 5 over x minus 3, our LCD is just x plus 1 times x minus 3. Now, my first fraction that has x plus 1 in the denominator has this first factor of the LCD, and that's taken care of, but it doesn't have an x minus 3. It needs to supplement by multiplying on an x minus 3 to get to the LCD. My second fraction has an x minus 3 in the denominator. It has this guy already, but it doesn't have an x plus 1. It needs to supplement with a factor of x plus 1 in order to get it to the LCD. And just like before, I have 3 over x plus 1, my initial fraction. I need to supplement with a factor of x minus 3 on the bottom. But of course, if I just multiply by like 1 over x minus 3, or just slap an x minus 3 in the denominator, that changes the value of the fraction. I need to multiply and divide by the same thing, so that net I'm multiplying and dividing by 1, or sorry, net I'm multiplying by 1, and I can get an equivalent fraction with denominator of the LCD. Same thing for my second fraction. 5 over x minus 3. This one has an x minus 3 in it, but it needs to pick up an x plus 1. We multiply that in the denominator, that factor of x plus 1, but again, we need to multiply by the same thing in the numerator as well, so that we don't change the value of that fraction. So we have an equivalent fraction, but it should have the LCD as its denominator now. Now I do the same step. I multiply before I add. So I'll take my first two fractions that are multiplied here, multiply them together. I multiply the numerators to get 3 times x minus 3. And I multiply my denominators. x plus 1 times x minus 3. To that I add my second two fractions. I multiply my numerators. 5 times x plus 1 over my denominators, x minus 3, x plus 1. Now at this point, I need to do a little more simplification. I note that I have common denominators. I have the same denominators in the first and second fractions. If I add the two fractions together, I can do that by adding the numerators. And keeping the same denominator. I do notice that multiplication is commutative, so x plus 1 times x minus 3 is the same as x minus 3 times x plus 1, no problem there. And here I need to be careful and make sure that I distribute everything carefully. So 3 times x minus 3 is 3x minus 9. 5 times x plus 1 is 5x plus 5 over my denominator. It might feel kind of cumbersome to keep writing the denominator over and over again when it's not really changing. I would recommend that you just be very careful and actually do write everything down in every step carefully. It does take, another 30 seconds or a minute or so to do the extra writing, but it's good to write it over and over like that, just so that you don't leave anything out. If you kind of get lazy and you just write like quotes or something like that, like, oh yeah, I know what the denominator is, you might make a mistake somewhere along the way and leave something out. Now in my numerator, I'm going to simplify. 3x plus 5x is 8x. I combine like terms. Minus 9 plus 5 is minus 4. So I have 8x minus 4 over x plus 1 times x minus 3. My denominator is already factored. I've got everything under one fraction and fairly simplified, but I do notice that in the numerator, there is a common factor of 4 in the first and second terms. I factor that out. I look for any common factors, and it doesn't appear there are any common factors in the numerator and denominator to divide out. So that's my answer. So I hope that you saw that the strategy is the same. The overall steps that we did were the same steps, but they just looked a little different because we have a binomial in our denominators now instead of just monomials or numbers. Now let's look at a situation like this one here and follow those same kind of steps. Here I have two rational expressions, two fractions with unlike denominators that I want to add together. What's my strategy? I take my two denominators. These ones look a little more complicated, but let's go with the same strategy. I take my two denominators, I factor them, I get the prime factorization, so to speak, or I factor my quadratics into hopefully two linear factors. X squared plus 3x minus 18, are there two numbers that multiply to 18 that have, or that minus 18 that have a sum of plus 3? I think that's plus 6 and minus 3, right? 6 times 3 is 18. So I think we have x plus 6 times x minus 3. X squared plus 8x plus 12, are there two numbers that multiply to 12 to plus 12 and that add to plus 8? I think that's 6 and 2. So I have a factor of x plus 6 that is also in the second one. So I'll write it below that one. I also have a factor of x plus 2 that's a new factor that I haven't seen before. I'll write it in its own column. So what's my LCD then? I see some x plus 6s floating around. The highest power of x plus 6 I see is the first power, so it's just x plus 6 to the first. I see an x minus 3 and an x plus 2, both to the first power, so they come down into the LCD. So my LCD is x plus 6 times x minus 3 times x plus 2. My first denominator has an x plus 6 and an x minus 3, but it needs to be supplemented with an x plus 2 to make the LCD. My second denominator has an x plus 6 and an x plus 2, but it needs to be supplemented with an x minus 3 to make the LCD. So my first fraction I want to multiply by x plus 2 over x plus 2. My second by x minus 3 over x minus 3. Instead of writing this as x squared plus 3x minus 18, I'm going to choose to write this in its factored form, which I figured out over there as x plus 6 times x minus 3. That's this first fraction. And again, to make the LCD, I need to supplement that with a factor of x plus 2. And again, if I'm going to put it on the denominator, I need to also multiply it onto the numerator. And then I'm going to just pop over here for the plus 4x over, and this denominator, x squared plus 8x plus 12, I'll choose to write as x plus 6 times x plus 2. So that's my original second fraction. But to get a like denominator, I need to supplement with a factor of x minus 3 on the bottom. And on the top as well. Now I need to multiply my first two fractions. 3 times x plus 2 is 3x plus 6 over my LCD over x plus 6 times x minus 3 times x plus 2. And then plus 4x times x minus 3 is 4x squared minus 12x. Again, I have the same denominator. So I just add the numerators, keep the same denominator. Let me simplify that numerator by combining together a couple of terms. I have a 4x squared minus 12x plus 3x is a minus 9x. Got those two, and then plus 6 over x plus 6, x minus 3, x plus 2. So now I've got everything added together, combined into a single rational expression, a single fraction. And I want to simplify. I want to factor the numerator and look for any common factors. So a times c is 4 times 6, or 24. So I'm looking for m times n equals 24, m plus n equals -9. So what are my candidates for m and n? 1 and 24. Remember, these should be the same sign, so these should be both negative numbers. I'm looking to add to -9. 1 and 24, they don't add to 9. 2 and 12, nope. 3 and 8 adds to 11 or -11. 4 and 6. That doesn't work either, adds to 10 or negative 10. 5 doesn't go into 24, and if I go to 6, I get 6 times 4. So these are all of my factors m and n that gives me m times n equals 24. Do any of them add to, if they were both negative, do any of them add to negative 9? No, they don't. So this quadratic in the top here is prime. It doesn't factor into the integers. So this is kind of like having 3 divided by 5 times 7 times 13 or something like that. We have a prime number over the product of 3 different prime numbers. There's going to be no common factor to divide out. Or if we have a prime polynomial over the product of 3 different prime polynomials, there's no common factors to divide out. So this is what we end up with. Okay, let's come over to the worksheet and let's go through these two. I think we'll save this one down here maybe as a warm-up for next time. But let's work through these two in the last 6 minutes or so that we have, and I will kind of work through them with you and then do a really quick recap at the end, and that will finish us up for today. Okay. So starting these two, I'll come in about 30 seconds or so. Was this the exact same one that I did over here? Did I?
Yeah.
Okay. Sorry about that. Every once in a while, I copy them over, and then I think a couple of times I've forgotten to change.
It's okay. I still did it wrong both times.
Oh my god.
Gonna say
I
these
still
numbers are wrong.
managed to fumble it somehow.
I think this is a new one though. So
Yeah,
focus
no,
on
it
the second one maybe.
See, my problem is I'm dyslexic, so sometimes I like read the problem too fast. Like my friend specifically was trying to help me like do these better, and he's like, "You keep like switching the exponents," and I'm like, "But the number's so tiny, I can't read it."
Oh, here I can zoom in a little bit if that helps.
No, my brain just processes it too quick and is like, "Ah, yes, that 2, that's a 3." That I like look back and I'm like, "Wait, no."
Yeah, unfortunately with the exponents, when they're in like a numerator denominator, yeah, it can get pretty small and difficult to read. Yeah. Okay, so well, we're about out of time, but just super quick recap. For the first denominator, 3x minus 3, we can factor a 3 out of there, 3 times x minus 1. For the second denominator, that factors as x minus 1 times x plus 4, two numbers that add to positive 3 that multiply to negative 4. We see the x minus 1 is kind of a shared factor between the two. So our LCD is 3 times x minus 1 times x plus 4. We need to multiply our first fraction. It has a 3 times x minus 1 already. We need to multiply it by x plus 4 over x plus 4. And our second fraction, this x squared plus 3x minus 4, already has an x minus 1 times x plus 4. We just need to multiply it by the number 3. So we multiply by 3 over 3. We keep the same denominator. We add the numerators, 2x times x plus 4 plus 5x times 3 over our LCD. And that gives us 2x squared plus 23x over our LCD. We could, I suppose, factor an x out of here and make it x times 2x plus 23 over 3 times x minus 1 times x plus 4. But we note that none of those factors divide out. So this is the simplest form.